work by the Ontario Energy Board to try to quantify the effect of the Energy East pipeline on greenhouse gas emissions. And so this is a project that's kind of evolved out of that initial bit of work that we did with the Ontario Energy Board. And we've now tried to offer a more generalized analysis of the link between pipeline infrastructure or new pipelines and global greenhouse gas emissions. And it's been an interesting project to be involved in because the ground keeps moving beneath our feet. And so we started this when the price of oil was well north of $100 a barrel, and it has since dropped by over half. And so the environment in the oil sands is completely different than it was when we started. Some of our analysis reflects that, and some we still have to catch up with the changes that have happened. Even just this week, there was a big announcement by Keystone, by the U.S. government. Keystone asked for a pause in its evaluation by the U.S. government, so that it could get the Nebraska government on side with its new with its changes in pipeline routing. And it sounds like there's some negotiation back and forth. And I think the latest announcement, which just happened yesterday, was that the U.S. government wasn't going to grant this pause, and so it was going to proceed with the evaluation of Keystone Pipeline probably by this year or next year. Anyway, so this is an ongoing bit of analysis. James, you can go to the next slide. I'll just start out by setting a little bit of context. And I think this is something that everyone on the line will be well familiar with. The oil production from the Alberta oil sands, even in the constrained environment that we're in with low prices right now, continues to expand. And the second point is that expanding oil production is responsible for most of the growth in Canadian greenhouse gas emissions. And it looks to be responsible for most of the growth in Canadian greenhouse gas emissions going forward. And so this figure at the bottom right of the slide shows it's a figure that Pembina Institute put together based on data from Environment Canada, or forecast from Environment Canada, I should say. And it shows the forecast change in greenhouse gas emissions at the Canadian level between 2005 and 2020. You can see that Environment Canada projects in the orange bar here that emissions are going to grow by about 20 to 30 megatons per year between 2025 and 2020. And that's really dominated by the oil sands, by growth in the oil sands. And so the projection from Environment Canada last year was that oil sands emissions would grow by 60 or 65 million tons a year through 2020. And so that would dwarf any reductions that we're seeing in other sectors, for example, in the electricity sector. And so there's concern, obviously, around greenhouse gas emissions in the oil sands. The second bit of context around this presentation is around the transport infrastructure that the oil sands require. And so Alberta is obviously landlocked, and so to produce oil, it needs some way to get oil to market. Alberta can't use all the oil it produces. And so this big increase in oil production that's going on in Alberta needs to have an accompanying increase in transport infrastructure. And as a result, there's been a real interest in the link between granting allowances for new pipeline infrastructure and the resulting greenhouse gas emissions from the oil sands. So basically the question is, if we build a new pipeline, or if we allow a new pipeline to go ahead, what's going to be the impact on greenhouse gas emissions? And James, you can go to the next slide. You can kind of get a sense of the concern from this slide that the Canadian Association of Petroleum Producers, this is the industry association, puts together every year. So this is the green at the bottom is the existing oil transport infrastructure. So it's dominated by the Enbridge main line and the existing Keystone pipeline. And then the yellow bars on the top are the changes in oil transport capacity that would be generated by approval and building of new pipelines. And so you can see that the Energy East pipeline is the biggest proposed pipeline out of the oil sands area. That's the top of the figure there. Would be about 1 million barrels per day. The Keystone XL pipeline is another one of the proposed pipelines. It's just under 1 million barrels per day. And then you can see the red line that's traced out is the existing and forecast production capacity in the oil sands. So right now, this actually is not exactly just the oil sands. It includes some conventional production in Alberta. It also includes some production of oil products in North Dakota, in the Bakken region. But essentially, you can look at the link between how much is produced, which is this red line here, and how much takeaway capacity there is from the region on pipelines. And that's the green and the yellow going forward capacity. And so the basic concern is that there's the concern on behalf of the industry is there's not enough takeaway capacity today, that's this green line, to allow significant increases in capacity going forward, which are projected to happen. And so, one of the ways we need to, one of the things that the industry is proposing is more of these pipelines to get this oil out of the landlocked Alberta region and North Dakota region. And on the other side, one of the strategies increasingly taken by those who want to see less supply from the oil sands is that let's cut off the takeaway infrastructure, the pipeline infrastructure, and that will be a way of limiting expansion capacity in oil sands. So James, you can go to the next slide. In this project, we're going to look at 4 proposed pipelines. These are the 4 big ones that you see them on the previous slide as well. So we're going to, and obviously I think everyone's heard of all these pipelines. The Keystone XL is the one we're going to focus on in a bunch of the slides that come forward. So that's this line that goes from Hardisty in Alberta to Houston in Texas. It's the red line. It's proposed by TransCanada. It would be about a $7 billion line. It would take away just under 1 million barrels per day of oil from the oil sands region to the Gulf Coast. The other big project that we're looking at in this analysis is the Energy East project. That's the green line that would take oil through Canada from Hardisty again, eventually to a refinery and a port in St. John, New Brunswick. And this would be this is the biggest proposed pipeline in the region. And it would have a capacity over 1 billion, or over 1,000 barrels per day. And it would cost upwards of $11 billion. And then there's 2 pipelines that are proposed to the west coast. The Northern Gateway pipeline would leave Edmonton and arrive in Kitimat. It's proposed by the Enbridge, and it would take away about 500,000 barrels per day. And then the TransCanada pipeline would twin an existing pipeline that goes from Alberta to Vancouver. So both of these would reach West Coast sea and would be taken away by tankers from the West Coast. And so we're going to be looking at all of these pipelines, trying to figure out what each of these pipelines individually and as a group would do to greenhouse gas emissions, both in Alberta as well as the rest of the world. So James, you can move to the next slide. And so essentially our question in this project, and I think it's a question that's quite relevant to the public policy debate right now, is whether new pipelines increase oil sands greenhouse gas emissions. And there's 2 very different sets of opinions on this. There's a bunch of groups, Pembina Institute, for example, in Canada, but the group 350.org, headed by Bill McKibben in the US, which are strong proponents of the idea that new pipelines are likely to increase greenhouse gas emissions. And so in Canada, Pembina has put out a series of reports around whether both Keystone XL and Energy East would be likely to increase greenhouse gas emissions, and have come down unanimously on the side that they would. So you can see a bunch of the quotes that I pulled out of reports, but they suggest that both Keystone XL and Energy East would result in higher prices for crude oil in Alberta, and those higher prices for crude oil in Alberta, so higher wellhead prices we call them, or netback prices for crude oil in Alberta, those would result in stimulation in investment in Alberta. And that stimulated investment in new oil sands project in Alberta would increase greenhouse gases. And there's a big quote that's been circulating from James Hansen, who's probably the foremost climate scientist in the world over his long career since the 70s, and has come out with this quote that Oil sands are game over for the planet if we exploit them fully, and that a pipeline like KeyXL would be facilitating this kind of game over state for the planet. And then on the other side, there's a bunch of analysis and project proponents that say, no, there's no likely increase in emissions associated with new pipelines. And so the Department of Environment hired a consultant called NSIS, who ran a bunch of numbers and ended up figuring out that the overall impact of Keystone XL on global greenhouse gas emissions would be basically nothing. And the analysis wasn't transparent. It wasn't, there's no ability for outsiders to see the analysis that NSIS did. But as far as I could tell, it was a model something similar to what I'm going to present to you today. But it wasn't, there wasn't much detail presented. TransCanada, the proponent of the Keystone XL pipeline, has said that Keystone XL, this is from their statement just a couple of days ago, would be safer and generate fewer greenhouse gas emissions than transporting crude by other means. And so they're saying that allowing these pipelines to go through would actually be something that would reduce greenhouse gas emissions. And there's a group called IHS-CIRA, which is a think tank in Alberta, which has come up with a similar claim as well, that Keystone XL and other pipelines would have no material impact on oil sands greenhouse gas emissions. And so this bit of work that I'm participating in here is trying to wade into this debate and offer an updated analysis, and I think a more transparent analysis and a more complete analysis that's been offered by other groups, and try to answer this question about whether oil sands pipelines actually will increase or reduce greenhouse gas emissions from the oil sands, as well as from other places in the world, and to try to put some numbers on it. Oh, look, I'm pressing my button and it's moving. James, you're reading my mind. So the basic way that us and other analysts are going about figuring out whether and by how much greenhouse gas emissions may change as a result of new pipelines is this equation that I'm presenting here. It's kind of a life cycle analysis equation. And so what this is saying is that a change in emissions, that's this delta E, so the change in emissions associated with new oil sands, is going to be calculated as follows. It's going to be the first part on the left or the right-hand side of the equation is going to be thinking about the change in emissions from the oil sands that are generated by new pipelines times the emissions factor, the life cycle emissions of oil from the oil sands. And then we're going to see how much, so we're going to count the total new emissions from the oil sands that are generated from this pipeline. And then we're also going to think about whether these oil sands displace oil that would have been generated somewhere else or produced somewhere else. And we're going to compare the emissions factor, that's this E, this wiggly E or epsilon, from the oil sands with the emissions factor from other places. And so the basic concern associated with oil sands is that this epsilon or emissions intensity of the oil sands is quite a bit higher than in other regions. And this is because the method through which we produce oil sands is pretty different than the method we produce oil in other regions in the world. In the oil sands region, there's two basic technologies for getting oil out of the ground. One of them is mining the oil. So this oil is not flowing in Alberta. It's caught up in the bitumen, or it's part of the bitumen. It's attached to sand, basically. And so one of the ways we can get it out of the ground is by mining it. We take big diggers, we dig it up if it's at the surface, and then we've got this slurry, this kind of bitumen that needs to be, that can't go into a conventional refinery. It needs to be upgraded before it can be sent to a regular refinery. And so the upgrading process basically heats this bitumen mixture or compound and removes the sand and produces a synthetic crude oil, which can be sent to a regular refinery. But this process of upgrading the crude oil takes a lot of energy. It requires heating the crude oil, which isn't something that other resources need to do. The other way that we extract oil from the oil sands is called with in situ production. In situ production basically involves injecting steam into the ground. So we heat water without natural gas. We inject steam into the ground, and that gets this bitumen mixture hot enough to flow to the surface. and then we can extract it that way. But again, we require a bunch of steam in this in situ process, which isn't required in other processes. And so as a result, the upstream emissions associated with new oil sands production, in other words, this epsilon with oil sands, the emissions intensity of oil sands, is quite a bit higher than the emissions intensity of other resources. And I've just put a couple of examples in a little table below. So you can see that the upstream emissions, and we call this sometimes well-to-tank emissions. So the emissions associated with getting a barrel of oil from the ground into someone's tank, tank in someone's car, the well-tank emissions, are quite a bit higher in the oil sands region than in other regions of the world. Venezuela uses a similar kind of technologies in the oil sands, and so has a relatively high upstream emissions as well. Whereas the Middle East has a much easier time getting oil out of the ground. It flows, it's a light crude oil, and it flows out of the ground relatively easily. And so the emissions upstream are much lower in the Middle Eastern region than in the oil sands or Venezuela. Then the right-hand column of the table is the total emissions, and that includes the emissions that happen when the oil in your gas tank is burned. And so we call these the well-to-wheels emissions rather than well-to-tank emissions. So that includes the combustion that goes on in the car. And the combustion that goes along in the car is pretty much the same no matter what source of oil is. It's the upstream emissions that are different, not the downstream emissions that are different. And so these total well-to-wheels emissions, or the life cycle emissions associated with these different crudes, are what we're going to look at as the basis for the analysis, but others have looked at as the basis for analysis. And the finding that this oil sands oil is much more intensive on a life cycle basis than other sources of oil around the world is the reason for concern. One of the main reasons for concern with building these new pipelines. If we're going to get out these emissions intensive oils and they're going to displace less emissions intensive oils in other regions of the world, then presumably global greenhouse gas emissions are going to go up. So James, you can go to the next slide. So there's been a couple of groups already that have taken this basic equation or basic method for analysis, life cycle analysis, and applied it to this question of whether new pipelines are likely to increase or decrease emissions from the oil sands. And I'll just walk through three that I've done relatively well. So the Pembina Institute has done a bunch of analysis of both the Energy East and the Keystone XL pipelines. And I'll talk about one of them. They produced an analysis of the Energy East pipeline last year, and they focused especially on just the first two parts of this equation on the right-hand side. So they're looking at if we build a new pipeline, and remember the Energy East pipeline is about 1,000 barrels per day of capacity, and 1,000 million barrels per day, of capacity. And so if we have 1,000 million barrels per day of oil sands capacity, and we know the emissions intensity of the oil sands, that's this epsilon, we can think about how much the greenhouse gas emissions in Alberta are likely to change as a result of facilitating all this new oil sands activity. And so Pembina found an estimate of somewhere between 30 and 32 million tons of CO2 per year on upstream emissions associated with this new pipeline, this new Energy East pipeline. So just to put that in perspective, Canada's total emissions are about 700 million tons of CO2 per year. So this is about 5% of Canada's emissions would be just tied up in this single pipeline associated with the upstream emissions. So what the next analysis I want to talk about is this U.S. State Department analysis around the Keystone XL pipeline. This is the kind of the famous analysis that there's a lot of debate over, and that President Obama has said, if the U.S. State Department finds a significant impact of the Keystone XL pipeline on greenhouse gas emissions, then that pipeline's not going forward. And so this is a really critical analysis. And so the U.S. state has taken a bit more of a broad view than the Pembina analysis that I just talked about. And they're looking at the comparison between not just the oil that would be the new oil that we brought on stream by the pipeline, by the approval of the Keystone XL pipeline, but also this right-hand term in the equation, which is what the other source of oil that would be displaced by the pipeline are. And so they make some assumptions about whether it might displace both either Middle Eastern oil or Venezuelan oil. And they assume that whatever new oil was brought on by the approval of the Keystone XL pipeline, if it was say 1,000 million barrels per day that was brought on, then that exact amount will be displaced somewhere else. And so they're basically comparing emissions factors of oil in the oil sands with oil in other places, just like that table I showed you before. And they find that if oil, if this new oil from the oil sands is displacing a relatively emissions-intensive oil like the Venezuelan oil, then the impact would be fairly small. And if it was displacing a relatively light footprint oil like the Middle East oil, then the emissions effect would be bigger. And then last year, another analysis came on basically critiquing the U.S. state approach of assuming that the change in production from other regions of the world would be exactly equal to the change in production in the oil sands. So that's this delta Q oil sands and delta Q displaced. So the U.S. State Department assumed those two would be equal. And the Stockholm Institute analysis, which was published in Nature Climate Change last year, basically said, well, that's a silly assumption to make, because as new oil is brought online in the oil sands, it's going to lower the price of oil, lower the world price of oil. And that lower world price of oil is going to facilitate or encourage more people to consume oil. And so you're going to see you're going to see an increase in consumption of oil on a world scale as a result of this new pipeline. And so there's no reason to think that these two delta Qs are going to be equal. In fact, it's likely that the increase in production in the oil sands is going to be bigger than whatever amount of oil is displaced in other regions in the world. And so as a result of that analysis, they find a much, much bigger impact of approving KXL on greenhouse gas emissions. So we're going to take the same approach, and we're going to go, can you move to the next slide there, James? We're going to do a couple of things. Rather than assuming what this change in production in the oil sands are, and what the change in production in other regions of the world are, and which oil resources are going to be displaced by the approval of one of these pipelines, we're going to try to estimate those. Sorry, my screen just went to a screensaver. There we go. And so we're going to build a new oil market model. We call it Oil Trends. It's going to be a kind of standard model for assessing the implications of something like new oil production. It's going to be a spatial equilibrium model that accounts for all the production of oil in different regions of the world, the transport of oil and oil products from one region to another, the refining of oil into refined oil, petroleum products, and the consumption of crude oil products. We're going to account for different transportation options and strategic oil market decisions and price responsive demand. And so in particular, what these prior studies did, most of these prior studies assumed that delta Q oil sands was equal to delta Q displaced. In other words, when a new barrel of oil is brought online in the oil sands, it's going to displace exactly 1 barrel of oil somewhere else in the world. That's what this U.S. state analysis does. And so we're going to try to relax that assumption and try to estimate it rather than assume it. And then the other thing we're going to do that's really critical is we're going to say all the other analysis has said when there's one other barrel a day of oil of pipeline capacity, we're going to assume that delta Q oil sands also increases by 1 barrel per day. And so that the amount of new oil sands production is going to exactly mirror the amount of new oil sands pipeline capacity. And that's an assumption, again, in previous analysis. And rather than assuming that, we're going to try to calculate it. So you can go to the next slide. And so how are we going to go about doing that? Well, we're going to try to estimate the change in production in the oil sands by modeling the effect of a new pipeline on wellhead prices in the oil sands region, and by having some sort of supply curve to try to reflect how costly it is to develop the next barrel of resources in the region. We're going to estimate how much oil will be displaced in other regions of the world with this integrated model of oil production, transport, and consumption from different regions that I just described, and I'll describe more. And then we're going to try to estimate which resource is going to be displaced and the emissions factor of the resource that's displaced using this global model as well. So I'll try to explain what this oil sands model does in a fairly short time. It's a model that takes into account the production, the transport, the refining, and the demand for crude oil. It models the transport between all different regions in the world. So we lump it into 27 different regions. And we're going to solve, we're basically going to have a partial equilibrium model. So it's an economic model that solves for the price of each different type of crude oil and different type of refined petroleum product. So I can answer more questions about the model, but I'll just go through it quickly. James, you could go to the next slide. On the production side, we try to account for 54 different resources. And so when I say resources, this would be resources that differ based on, so they're all oil resources. They're resources that differ based on the sulfur content, for example, or the density of the greenhouse gas intensity. And so, for example, conventional crude oil in Alberta would be one resource, and oil sands mining would be another resource, and oil sands in situ would be another resource, and Middle Eastern light would be another resource, and Venezuelan ore emulsion would be another resource. And so we have these different resources that depend on the geology in different regions in the world. And then we have oil producers that try to figure out whether they should invest in production capacity. They do that based on this assumption that they're trying to just make decisions in order to maximize their profits. You can go to the next slide. Okay, so once we've figured out whether an oil sands producer is going to produce oil in a region or not, they have to get it somewhere. And this is the big question in Alberta, is how they transport, how the oil is transported to market. And so our model accounts for two issues. It accounts for whether to build new transport infrastructure, new pipelines in particular. And there's both an economic and a regulatory aspect to that decision. And so the economic one would be whether the proponent of a pipeline thinks they can recoup the cost of a pipeline in pipeline tolls. And those, and then the regulatory decision would be based on whether the regulator lets the pipeline go ahead. And so you could think of this decision about whether to build a new pipeline being like an arbitrage decision. If there's a big difference between prices in Alberta, say, and in Oklahoma, then it looks favorable for a new pipeline proponent to build a pipeline between those two regions because they'll be able to have relatively high pipeline tolls and recoup some of the investment. The second stage of our transport decision is that once the transport infrastructure is in place, and transport infrastructure includes not just pipelines, but also rail and shipping infrastructure. So once the transport infrastructure is in place, then we make a model in which profit maximizing firms use the existing transport infrastructure to transport oil around the world. And these different transport options, pipeline, rail, and shipborne tanker, or seaborne tanker, differ in their cost, their greenhouse gas intensities, as well as their availability. So just to give you a sense of the costs, to take oil out of Hardisty, Alberta, to Cushing, Oklahoma, and this is where the West Texas Intermediate Oil is placed, it's the main hub in the eastern U.S., to take it by pipeline costs around $5 to $7 a barrel. To take it by rail costs around $15 a barrel. So this is the essential reason why Alberta wants to have more pipelines from Alberta to Cushing, Oklahoma, because right now the producers get about $8 to $10 less per barrel shipping by pipeline than they are shipping by rail than they would ship by pipeline. If they take the same oil from Alberta and ship it to Vancouver instead, it costs a lot less because the rail line is a lot less, shorter, sorry. And shipping by sea, which is ends up being very cheap, $1 or $2 a barrel to ship it halfway around the world. And this is why Alberta wants to get its oil at sea, because once it's at sea, it essentially is costless to ship it no matter where in the world. Okay, so once oil arrives at a destination, it undergoes refining. Refineries take various grades of crude oil and turn it into different refined petroleum products like gasoline and diesel. And then there's different refineries, existing capacity, different refineries around the world that have different abilities to turn different types of fuel stocks into different types of refined petroleum products. Refined petroleum products, like crude oil, can be transported into between different regions, but there tends to be much less transporting of refined products than of crude products. Go to the demand side. Demand side is fairly straightforward. We assume that consumers in each region respond to changes in petroleum prices, and this is surprisingly something that other analysis hasn't done so much. And so we assume that if the price of an oil product goes up in a region, that consumers consume less of it, and conversely, if the price of an oil product goes down in a region, consumers will consume more. Okay, so we built this spatial equilibrium model that's has these different agents all around the world, and we're trying to figure out what the effect of allowing this pipeline would be on global greenhouse gas emissions. I'm not going to go through this. This tells a little bit about how we solve it in the data, but we can talk about that after if you like. So you can go to the next slide. So basically what we're going to do is look at these 4 different pipeline projects and consider them each independently. So we're going to say, what happens if the regulator, for example, the US State Department says, yeah, Keystone XL can go ahead? Or what happens if the National Energy Board or the provinces say Energy East can go ahead? So we're gonna simulate that decision in our model, and we're gonna try to analyze. We're gonna look at the change in greenhouse gas emissions and other factors that go on between this scenario where the pipeline is approved and the scenario where the pipeline isn't approved. There's obviously lots of other factors that affect greenhouse gas emissions in addition to this pipeline decision. We're going to hold those constant between these 2 different scenarios, but there's lots of sensitivity analysis. For example, what the cost of rail is, or how demand elastic consumers are, or what the price of oil is, that also go into affecting what our calculations are. So we're doing some sensitivity analysis. I'll present a little bit, but there's obviously lots of uncertainty in the analysis we're doing. You can go to the next slide. Okay, so I just want to present one of the slides from our reference case analysis first before going into the results from these pipeline scenarios. This is a projection from our model of what the production from the oil sands would be and what the transport would look like from the oil sands in the absence of any new pipeline approval. And so this looks a little bit like the figure I showed you at the very beginning from the Canadian Association of Petroleum Products, but they assume a whole bunch of new pipelines get built. In this scenario, we're assuming no new pipelines get built. So this is our reference case scenario. And what it shows is that if no new pipelines get built, our model is suggesting that rail would expand significantly in capacity and start taking away upwards of 2 million barrels per day from Alberta. And so this is something to keep in mind, that our reference case scenario sees a really large growth in rail from the region. Currently, rail in the region is less than 1 million barrels per day, significantly less than 1 million barrels per day, although it's grown quite a lot in the last couple of years, as I'm sure you've heard in the news. But this really fast growth in rail takeaway actually has a parallel. And so if you look at North Dakota, which is the region just south of Alberta, rail transport capacity grew at quite a bit faster than the rate that our model's projecting between 2010 and 2013. And so they're likewise, just like Alberta, North Dakota's background region is very transport constrained, and so is increasingly shipping oil by rail rather than by pipeline. And so, although this is just a scenario for our model, this big expansion in rail, it looks like it may be plausible with a recent parallel in North Dakota. Okay, so what happens when this Keystone XL pipeline gets approved? Well, first of all, it gets approved, it gets built. It looks like it's economic to build it, and so when the regulator says it gets approved in our model, then the model goes ahead and builds it. So what we see is 3 distinct phases that our model shows. What we see initially is that there's a big premium for a big increase in the wellhead price of bitumen in Alberta, and that's this in the first few years after 2020. That's this pink dashed line you see in the figure. And the reason we see a big increase in wellhead prices in Alberta is because all of a sudden that they're transporting oil not by so much anymore, but increasingly by pipeline. So you see some of that difference between pipeline costs and rail costs accrue to the producers in that region. And so the wellhead price goes up in Alberta, and that spurs on new investments in oil sands in Alberta, just like it's supposed to. In the middle period there, this green shaded period, what we're seeing is that the price for bitumen in Alberta dropped a whole bunch. And the reason is that shipping bitumen out of Alberta requires something called a diluent. So the bitumen won't flow in a pipeline on its own. It's too dense, or it's too viscous. And so it needs to be diluted with something to make it less viscous. And so that thing can be some other type of petroleum liquid, and typically it is a light much lighter, much less dense, much less viscous petroleum product, like light crude oil, for example. And what we're seeing is that in that middle period, a few years after the Keystone XL pipeline's built, Alberta needs to import a whole bunch of diluent in order to be able to ship out its viscous bitumen. And so the price of bitumen in Alberta ends up dropping a bunch because now you have to pay to import diluent because Alberta hasn't got enough on its own to deal with this rapid increase in the export of bitumen. And so that ends up pushing down the wellhead price of bitumen in Alberta a little bit. And then somewhere around 15 years or 12 years after the pipeline gets built, the pipeline network gets full. And so once the pipeline network gets full, we don't see such a premium for the price of bitumen anymore. And I'll talk about that a little bit in a minute. And so we see that the pipeline really contributes to increased wellhead prices in Alberta over a 10-year period or so in our model. You can go to the next slide. And it's during that period when prices are higher that you're going to encourage more production. This is a summary of our global estimates for greenhouse gas impacts of the Keystone XL pipeline. And so you can see that this is kind of a figure with a lot going on, but we've aggregated these 27 regions in our model to a much more manageable visually 6 or 7 sets of regions in our model. And so what you can see is in each region, we've tried to estimate using our model the impact of approving Keystone XL on emissions from extraction, on emissions from refining, on emissions from oil transport, and on emissions from oil consumption. And so what we're seeing is that in Western Canada, or in Canada, emissions from oil extraction, refining, and transport are increasing as a result of this pipeline. But to some degree, they're being displaced in other regions, and this is what you'd expect, right? If we're starting to extract more and refine more products in Canada, then we're going to extract a little bit less and refine a little bit less in other regions of the world. And we're also seeing that consumption of oil products is going up in a bunch of places, and notably in China. And so this is the destination for a lot of the net oil that's being brought online by Keystone Pipeline. In total, we're estimating that approving Keystone Pipeline looks like it would increase global greenhouse gas emissions by somewhere around 15 million tons per year. So not too far off the high end of the state analysis, the US state analysis. Go to the next slide. So I just want to bring you back to what we were trying to do and how we compare it to what other people have done. This basic equation says that we're figuring out the emissions from the new emissions from improving one of these pipelines by thinking about the total emissions intensity and the new production of oil that's brought on stream to oil sands, and then thinking about what oil is displaced in other regions and the emissions intensity in other regions. And like I said earlier, one of the big assumptions that all the previous analysis makes is that the change in production from the oil sands equals the pipeline capacity. And what we're suggesting in our analysis is that that's an assumption. It's not based on an economic model, and that it looks like an overstatement, that the change in production from the oil sands actually looks like it would be quite a bit smaller than the change of production for pipeline capacity, or the change in total pipeline capacity. And I'm just going to hold that point, and I'll talk about it again in a minute. Like the analysis the Stockholm Institute presented, we're finding that the amount of oil that will be displaced in other regions of the world actually looks like it'd be quite a bit smaller than the new oil that we brought online in Alberta. And this is, again, just for the reason that analysis highlighted, is that then bringing new oil on in Alberta reduces the global price for crude oil and encourages consumers to consume more crude oil. And like the other analysis that's been done took an agnostic stance on which oil would be displaced, we're finding in our analysis that it looks like the marginal barrel after the Canadian crude oil looks to be coming from Venezuela. And so when we increase crude oil production in the oil sands, we're going to be displacing mostly Venezuela oil, which has a relatively high emissions factor. And these are the kind of factors that are going into our analysis, the results from our analysis. James, maybe I'll just make a couple of quick points, and then I realize I've been going on quite a while. But you can go to the next slide. I think I'll skip this, and we'll go to I'll maybe come back to it in questions. I'll skip this as well, and I'll just finish off with this one. So our analysis, what I've been talking about to date, just looks at the KeyXL pipeline. We've done the same kind of analysis for the two pipelines, the other three pipelines that have been proposed. Our analysis of the Energy East pipeline comes out with a somewhat similar number, a little bit smaller overall number on effect on greenhouse gas emissions, global greenhouse gas emissions than our Keystone XL pipeline. And that's primarily because the Energy East pipeline is a less economic pipeline. it's a longer pipeline than the Keystone XL pipeline. It costs more to build. And as a result, the increase in the netbacks or the wellhead price in Alberta is smaller than the Keystone XL pipeline, and so that gives less of encouragement for new investment in the oil sands as a result of pipeline approvals. That's why we see a slightly smaller number in the Energy East case. If we allowed expansion or generation of both allowed the construction of both the Northern Gateway, that's this NGW, and Trans Mountain Express, that's the TMX. So those are both the pipelines to the west coast of Canada. Our analysis suggests an increase in annual emissions more like 25 million tons a year, and that's substantially because the capacity of both those pipelines together is relatively large, but also because they're economic pipelines to build. They go a very short distance, and so they generate high netbacks to producers in Alberta and a large incentive for new investment. So I know I rushed a little bit at the end there, but I think I'll end there, and that'll allow some questions before we have to end. So thanks very much. I hope that was not too confusing.
Okay, thanks, Nic. That was great. Excuse me, one thing I realized is I never gave Nic a proper introduction at the beginning. So just to say that he's a Canada Research Chair and an economist at the University of Ottawa. I'm sure many of you know him already, but anyway. So what we'll do now is pass to a kind of question and answer or discussion period. So people can ask questions on the mics. Or you can also send in written questions on the chat function. So just to remind you, the chat function is on the right-hand screen, and at the bottom there's a little window where you can put your cursor in and type. And if you would like to ask a question on the mics, just below the list of participants on the left, that you'll see a little hand. If you click that hand, what will happen is that I will be able to see that you want to speak, and I can unmute your mic and so on. So we'll open it up. And while we're waiting, maybe Nic, I'll ask a question then, since as we're waiting to see what other people type in for us. If you go right back to the beginning, you had the Stockholm Institute, and you had Pembina, and you had the US State Department. So I'm wondering, how do your results relate to those three? Particularly, I think the Stockholm Institute had a huge number. It was like 100.
Yeah.
Why are they so big? You don't seem to be quite that big. So I'm wondering what the difference is there.
Okay, so first of all, go to the next slide. Okay, so this is the comparison with the other results. The other results are on the right-hand side. On the figure here. So this is Ericsson and Lazarus is the Stockholm Institute. The US state is the right-hand side. And then our results with some sensitivity analysis are on the left-hand side. And so one of the critiques we have of other models is that they make assumptions about what the changes in production in the oil sands are likely to be as a result of new pipelines. Both Ericsson and Lazarus, which is the Stockholm Institute, and the US state assume that if oil pipeline capacity increases by 1 million barrels per day, oil production will increase by 1 million barrels per day. To our mind, that's an assumption, and we don't think it's a good assumption. And we try to relax that assumption by doing an analysis around the economic decision to invest in new production in the oil sands, and that's part of what our model does. And what the implicit claim in Ericsson, Lazarus, and the US state is that there's no other transport available from the oil sands region to other regions in the world. That's why oil sand production is increasing 1-for-1 with oil sands takeaway capacity with pipeline. And so it actually, at least the last few years' experience, suggests that rail actually looks like the transport choice that would be made if pipelines didn't exist. And we try to model the cost of rail leaving Alberta and find that if this pipeline wasn't built, then a lot of the oil would have been taken away anyway by rail. The price would have been lower and the investment wouldn't have been as high in the oil sands, but a lot of the oil wouldn't have been taken away, anyway. And that's why we don't see this one-to-one relationship between new pipelines oil production capacity in the oil sands. And that's the main reason why our results are much lower than those of the Stockholm Institute. So we do actually run, you can see the right-hand column here is no rail scenario in our model. And so we eliminate any new rail capacity going forward and simulate the results then. And we get a much closer number then. We find out about 60 million tons of greenhouse gas impact per year as a result of approval of Keystone XL. Still smaller than Ericsson and Lazarus. And I've actually had a little bit of a loss to explain why that is right now. So I know we thought about it, and I can ask my co-authors.
Okay. Well, there's a resounding silence from the chat line at the moment. I'm not seeing anything that people are asking. Seems to be a very bashful crowd. Well, I can ask you a kind of unfair question then, which is really about what do you think, what are kind of the political consequences, do you think, of your analysis?
Yeah. So I think that's a good question. I mean, I think first of all, what's the policy relevance?
Yeah.
What are the political consequences? I mean, so I think that there's an appetite by the public and by policymakers to have a good sense of whether these projects are likely to increase emissions or not. And I think the existing analysis, the State Department analysis, is incredibly thorough and quite transparent, but it makes a lot of assumptions about these variables that I don't think are that are well justified. And so what we're trying to do is conduct an analysis that uses kind of standard economic methods to try to assess what the results of these pipelines are. And so hopefully it will contribute to this debate about whether these oil pipelines do indeed increase greenhouse gas emissions and by how much. And the results, if politicians are serious when they say we want to know whether these pipelines increase greenhouse gas emissions before approving them, then and hopefully this kind of result would impact their decisions. And so Obama has basically come out and said, I don't want to approve Keystone XL if it's going to increase greenhouse gas emissions.
And what you're saying is it does increase.
Yeah,
greenhouse
it looks
gas.
like it. Our numbers actually come out more or less the same as the State Department numbers for different reasons. We think that the State Department left out two things, and those two things kind of counteract each other. One is that they left out the fact that new oil from Alberta will actually increase global consumption of oil, and the other is that the pipeline is likely not to increase oil production one for one. And those two things in our model seem to, those two, I think, wrong assumptions seem to cancel each other out.
Okay.
And we generate more or less the same results as the State Department.
Okay. So now it's lit up a bit. I have Carol Hunsberger, who I'm going to unmic. Hi, Carol. I think you can go ahead.
Hello. Can you hear me?
Yeah.
Okay, great. This is Carol Hunsberger from the University of Western Ontario. Thanks a lot, Nick. That was really interesting. I was wondering, your slide that had the map showing the differences in emissions projected in different regions of the world, if I interpreted that right, it looked like there would be a pretty big drop in emissions from refining in the US if Keystone went through. If that's correct, then can you explain why that would be? Isn't the whole point of Keystone to refine this diluted bitumen in the US, and wouldn't that lead to an increase in emissions?
I can't explain that to you right now, I don't think. But that's a really good question. I mean, the thing that we find when we look at this is that there's real knock-on effects with these kind of spatial equilibrium models. And so when we kind of simulate a new pipeline happening between Canada and the US, we also see big changes in transport and production all over the rest of the world as well. So we're seeing, it looks like the net change in refining is happening in China. And so what I would interpret that as is that the oil reaches the Gulf Coast and is transported in crude oil form from the Gulf Coast to China, where it's refined there. I know there's heavy oil refineries in the U.S. Gulf Coast as well, and so some of it's presumably refined in the U.S. Gulf Coast, but it could be displacing other oil, which is then refined in the U.S. in China and North Africa.
Okay, it seems like a long way to go to ship it to China to go through the Gulf Coast. But,
Yeah. So again, I mean, the cost of shipping is trivial. It's the cost of transport over land is the material cost. But again, one of the challenges with these models is that they spit out an inordinately large number of numbers, and so interpreting every change is difficult.
Right. Okay. Thank you.
Looks like Stefan has a question. Can I go ahead and I'll maybe talk to Stefan's question? I can't hear you, James. You're on mute.
Sorry. Stefan says, can you explain what drives the result that only 25% of pipeline capacity is used, and how sensitive the results are to the assumption of OPEC lowering production to keep prices high? That's not what OPEC is currently doing.
Okay, so let's go, I think it's, I can't remember if it's forward or back in the slides. Maybe forward.
Where are we going?
Oh, backwards. There, there, that's what it is. So this is the slide I didn't walk through. So the results don't show that only 25% of pipeline capacity is used. The pipeline indeed fills up. I mean, these pipelines aren't built without shipper support, and so the pipeline won't be built unless they've got some agreement to fill it up. So the pipeline in our model does get filled up. The claim that I'm making, or the results that our model show, that the increase in production from the oil sands is only about 25% of the new oil pipeline capacity. And so this is because, especially because, not only because, but especially because oil is getting displaced from rail and instead going on to pipelines. And so this is what this figure is showing here, that that the impact of a new pipeline, given that there's, or in the presence of alternative rail transport, is different than if you assume there's no alternative rail transport. And so for those of you that like supply and demand diagrams, if we had a existing kind of oil transport infrastructure that did not include rail and did not include a new pipeline or was transport constrained, we'd be at this Q1 quantity on our diagram. If we then approve a new pipeline, we're going to move over to Q3, right? We're going to shift the production capacity. However, if the original situation is that we're shipping oil by rail, we're going to be at Q2. So the difference between Q2 and Q3 is going to be driven by the difference in cost for rail and pipeline. And when we approve the new pipeline, we're going to increase production capacity in the region, and the amount that we increase production capacity is going to be driven by the difference in cost between pipeline and rail. And so, again, I just want to confirm that we're not assuming, or we're not finding that the pipeline is only 25% full. We're just saying that in our model, it only looks like the increase in oil production in the oil sands region is 25% of the pipeline capacity, roughly. And I would put some big caveats around the precise numbers that we're finding. There's lots of sensitivity analysis that I haven't shown here that suggests that our results are, quite variable, depending on the assumptions that you make. But that's the reference case result that we find. In terms of OPEC, we actually, we set out criticizing these prior studies, saying, you missed the role of OPEC. It doesn't actually look like it influences our model results very much. We model OPEC as a cartel. We don't model a price target. I agree with you that OPEC's strategy seems to have changed recently, or Saudi Arabia's strategy seems to have changed recently. And I think even prior to this year, there was academic articles suggesting that OPEC was acting more competitively than as a cartel. But we actually don't find a big response in our results to assuming that OPEC acts competitively versus to having it act as a cartel.
Okay, thank you very much, Nic. So we're just about out of our allotted time. So last chance if anybody wants to ask any question. Okay, doesn't seem like it. So anyway, Well, thank you very much, Nic, for an interesting presentation. We will be posting eventually the video of this because we recorded it on the website for people who missed it. We'll also be continuing this series of webinars. The next one, which is next week, is actually going to be me talking about whatever happened to carbon capture and storage and is it dead? And we'll be announcing more titles as we go forward. So thanks everybody again for participating, and thanks Nic for a very interesting presentation.
Thanks James, and thanks everyone for giving up a sunny lunch.